Afternoon and hello. Some of the most common angles we find in physics are 0, 30, 45, 60, and 90. They pop up a lot. And we can find the sine, cos, and tan for them without using a calculator, which is really cool because it speeds things up and it's actually more accurate because calculators only give things to a fixed number of decimal places, a fixed number of significant figures. So what I want to do here is move along here to, and that's with me, by the way. First of all, I want to draw up a table to post the results in. So we've got the angles, 0, 30, 45, 60, and 90. And we have the three main trig functions that we use, sine, cos, and tan. So what we'll do now is shrink it and put it to the bottom and gradually fill it up. First of all, let's draw up a triangle that almost, but not quite, exists. And that angle is being considered as 0. Very hard to draw a triangle with 0, so I'll draw one with a slightly bigger angle, and we'll pretend it's 0. Call it 0, which means the opposite height is going to actually be 0. We haven't drawn 0, but we can pretend. The adjacent is whatever it is, some non-zero value, and the hypotenuse is also a non-zero value, but it also happens to be the same as the adjacent because the angle is 0. Those two lines lie on each other. So we put that there. Sine of 0, now we're ready to go. Sine of 0 is opposite over hypotenuse, which is 0 divided by a non-zero number. And sine of 0 is 0. Let's post that. Cosine of 0 is adjacent over hypotenuse, but the hypotenuse is the adjacent, same length. So the cosine of 0 is the same number divided by itself, which is always 1. Let's post that. Tan of 0 is opposite over adjacent, which is again a 0 divided by a non-zero number, which will always be 0. We can post that. So that's the 0 done. Another triangle that almost exists is one with an angle of 90 degrees in it. It's pretty tricky to draw that. So I've drawn a slightly smaller angle, but we'll pretend it's 90. The top angle we'll pretend is around about 0. So that means the bottom one, the adjacent at the bottom there, is 0. The opposite is whatever it is, and the hypotenuse will actually be the same number as the opposite. So the opposite and the hypotenuse are equal to each other. Sine of 90 is opposite over hypotenuse, which is hypotenuse divided by hypotenuse, and that gives us 1, so we can post that. Cosine of 90 is adjacent over hypotenuse, which will be 0 divided by a non-zero, which is 0. We'll post that. Tan of 90 is opposite over adjacent, which is the opposite, whatever it is, divided by 0, and there we hit a problem, a snag, a real bit of a difficulty here, because we finish up with a tan of 90 producing an undefined situation, and a calculator will give you a maths error, syntax error. You'll break the brain of the calculator somehow. So we can post that. So for 0, 0, 1, 0, 90, 1, 0, undefined, no number exists. Now let's move on to triangles that actually exist. First one will be a right isosceles triangle, and I'll draw it there. Side lengths are 1, and I'm putting them in there, calling them the opposite and the adjacent, and you can tell which angle I'll be working on. And the two non-right angles are 45 degrees. Let's look at only one of them, the bottom left. There it is. Using Pythagoras, or as the Greeks say, Pythagoras, we got the hypotenuse squared is opposite squared plus adjacent squared. Hypotenuse squared is 1 squared plus 1 squared. Hypotenuse squared is 2, so the hypotenuse is the square root of 2 in meters, and that's perfect. A rough kind of sort of approximation is 1.414ish, and we'll leave that there, but I'm going to take it away and just leave it as root 2. Now, sine of 45 is opposite over hypotenuse, 1 over root 2, which is perfect. A rough kind of sort of approximation, which you can write in if you wish, but I think 1 over root 2 is better. And the decimal thing is around about 0.707. We can put that in. Cosine of 45 is adjacent over hypotenuse. Well, the adjacent's 1 as well, so the rest of it follows on the same. And the cosine and sine of 45 are the same number by symmetry, and both of them are 1 over root 2. Perfect. I know of almost no physics teachers who will be upset if you leave it as a fraction or a surd, 1 over root 2. Tan of 45, sorry, we'll post that. Tan of 45 is opposite over adjacent, which is 1 over 1, which is 1, and that's a nice little check too for when you want to make sure your calculator is not in radians. Put the tan of 45, if it's 1, you know your calculator's in degrees. Cool, 0, 45 and 90 degree covered. Let's move along to 30 and 60. We'll start with an equilateral triangle. Side lengths 2 meters, centimeters, miles, kilometers, nanometers, furlongs, parsecs, whatever you wish. And then we can rotate it so the right hand side is vertical. And then we can cut it in half horizontally. What that will do is that will give us the sort of triangle we're looking for. The original angles were 60 and the original lengths were 2. So if we remove the bottom half, we change the right hand height from 2 down to 1. And we also put in the right angle because we had a vertical line which is chopped in half. So that's will produce a right angle. Perfect. Using Pythagoras, or as the Greeks say Pythagoras, we can get the length of the remaining side. Length squared plus 1 squared is going to be 2 squared, so therefore length squared is 2 squared minus 1. Length squared is 3. The length we're looking for is a square root of 3. Perfect. Which is roughly kind of sort of about 1.732. Better to leave it as a square root of 3. Let's put in the 3 angles. Well, the top right hand corner was 60 degrees, it's still 60 degrees. The bottom left corner was 60 degrees, it's been cut in half, it's now 30 degrees. So we're now ready to find the sine, cos and tan of both 30 and 60 because we have a right angle triangle with those angles and all 3 side lengths known. Marvellous, we're away. 30 degrees. Sine, the opposite is 1 and the adjacent is root 3, which is around about that, but root 3 is better. Sine of 30, opposite over hypotenuse, 1 over root 2, half. We can post that. Cosine of 30 is adjacent over hypotenuse, which is root 3 over 2, and that's perfect. It's better to leave it like that, but if you wish to go decimals, it's around about 0.866. We can post that. Tan of 30 is opposite over adjacent, which is 1 over root 3. Perfect. Leave it like that if you can. If you can't, then you have to have decimals, around about 0.5773-ish for memory. We can post that. Now let's look at 60 degrees. That means that the 1 meter side is the adjacent, because the top right hand corner is the one we want, and the 1 is adjacent to it, the hypotenuse remains, and the opposite is now square root of 3, round about that. Sine of 60 is opposite over hypotenuse, root 3 over 2, perfect, leave it like that if you can. If not, move along to the decimals, which is around about that as before. Cosine of 60 is adjacent over hypotenuse, which is 1 over 2, wonderful, half, we can post that. Tan of 60, opposite over adjacent, root 3 over 1, or root 3, perfect, leave it like that if you can, but if you must, put in a decimal 1.732. And interestingly, some folk get stuck on the fact that trig functions, like the sine and cos, can't be bigger than 1. They can when you're dealing with tan. So we can post that, and now we can bring the summary back to full size. And there it is. Sine, cos and tan are all the right numbers and all the right sizes. Wonderful.